cryptography standards. Standards are always crucial, and that become the basis for proper implementation as well as compliances. So public key cryptography standards, PKCS, especially in RSA, play a very important role. Based on that, many more sophisticated implementations have evolved over time. The agenda for today's cryptography standards, then we will be discussing on PKCS format. Then we discuss on the algorithm that need to be to ensure that PKCS format is being properly implemented on the sender side and receiver side. That we discuss under optimal asymmetric encryption padding, OAEP. Then we will have a look at OAP procedure both on sender side and receiver side. Learning objectives for the course are: after attending this session, you shall be able to explain the public key cryptography standards. You should be able to describe PKCS format. You should be able to describe optimal asymmetric encryption padding, OAEP, and you shall be able to explain OAP procedure on sender side and also on receiver side. How does public key cryptography and RSA work? The public key cryptography and RSA work by using encryption, decryption, and key generation. Let us say we have Alice as a sender and we have Bob as a receiver and Eve as a cryptanalyst or the person who is trying to attack the ciphertext that is getting exchanged between sender and receiver. At that time, the Eve, who is actually cryptanalyst or the hacker, in RSA uses modular exponentiation for encryption and decryption, and he needs to calculate the eth square root of C mod n function. How RSA is working? Using encryption, decryption, and key generation. When we try to send the message P, this message P has been split into many blocks like M1, M2, M3 like that. We are considering the MI block which is in the plain text. This MI block, which is a plain text, will be converted into digital form, which will be combination of 0, 1 and which will be of fixed length. So this particular, the plain text has to be converted into the ciphertext. To arrive at the ciphertext CI corresponding to the plain text MI, we are having the exponential function for MI exponential mod n, and the remainder plays very important role in mod operation, and plus and multiplication operations have been carried out. In order to carry out this particular activity, on the receiver side, the decryption algorithm will be having the formula to recover the message. In addition to that, the another activity the receiver will be doing is generation of the uh, the encryption key and decryption key by making use of prime values or prime numbers P and Q. And by picking up prime numbers P and Q, by making use of the algorithm, encryption key E and D will be generated. D will be kept with the receiver and E will be made public. So the multiplication of P and Q, which is N, and the encryption key E, both will be made public, and those will be available to the sender as well. Sender, by making use of E value and multiplication of prime numbers P and Q, which is represented as N, and also by taking the plain text block MI, carries out the ciphertext, the encryption process by applying the formula MI to the power of E mod N. Because of this, we get CI, which will be transmitted over ciphertext. Now, this ciphertext which we are sending must be having higher level of security. And the hacker or cryptanalyst, if he is going to catch hold of this ciphertext, from that he shall not make any sense. He shall not be in a position to convert it into the original text so that he can use or misuse it for his intentions. So the overall thing is, we are interested in how can we provide this extra security for the message that is getting exchanged between the sender and receiver. So that is what we are trying to focus there, and for that purpose, how the RSA works, the knowledge about them is very crucial. In order to do it, the application of public key cryptography, we have to understand the overall objective is to provide the message confidentiality by making use of mathematical functions based on prime and Euler's algorithm and Euclid's algorithm. We try to ensure it is not as simple as a private key cryptography, because it is using here in public key cryptography we are using prime numbers, and we are also using the exponential and polynomial functions involving many multiplications, and also by making use of two keys. And higher level of security we provide by using digital signatures to ensure message integrity. And also we want to provide, by making use of digital signatures, authentication and non-repudiation. And we implement authentication at the protocol level. Sender and receiver shall agree upon very stringent rules about exchanging of the public keys, private keys, as well as encryption formula and decryption formula. When we are trying to implement all such things like ensuring confidentiality of the message, authentication, protocol authentication, all such things to provide security to the message that is getting exchanged between sender and receiver by making use of encryption and decryption, and which is involving private key and public key, we face a lot of practical issues. First issue is generating primes and test primality. Second one is the different types of attacks that may be taking place on the message which is getting the exchange over insecured the cyberspace or communication channel. And public key cryptography involves generating and prime using primes and primality test to check any given value is a prime or not. So those play very crucial role. If anything is happening without involving prime and product of two prime numbers, then the security will not be of higher order, because the product of prime numbers cannot be factored back. Factorization is always a tough time as far as the product of two prime numbers are being used. So we are testing whenever any value is getting transmitted, always we try to make use of prime numbers in public key cryptography. So prime number based higher algebra plays very crucial role here. So how to carry out primality test and other things, that is also very crucial. It determines whether or not a given number is prime, as opposed to actually decomposing the number into its constituent prime numbers. And there will be different types of attacks that will be taking place on the message by making use of modulus factorization, where the very mathematical operations that are being used, they become the focus. The hackers trying to identify the mathematical formula that are being used, and they try to hack the system to get unauthorized access to the message which is getting exchanged between sender and receiver. However, it is not so easy, because since public key cryptography is using primary keys and exponential operations. And next one is small exponent attack. So a lot of trial and errors will be done, and based on this, the attacker is trying to catch hold of this, and this is practically being implemented and followed by many hackers. Third one is side channel attacks. By using watching the pattern of the operations of the sender and getting the information and rebuilding it and trying to use it. That is what is happening here. So these issues, if we do not address properly, then the security that we provide for the message will not be of higher order, and the very public key cryptography is at stake. So we try to attempt to give higher order security for the message that is getting exchanged. So usually the hacker calculates the ETH root of C mod n, and RSA uses modular exponential for encryption and decryption, but attacker use the ETH root of C mod n. And when this information is getting exchanged in public key cryptography, key size and speed, a lot of trade-off we have to make. As the key size increases, the time required for key generation, time required for encryption, time required for decryption goes up in the scale of 10 raised to power of orders. So we have to address both these aspects. We have to ensure that if the smaller key size, then security will be less. If larger will be the key size, then the entire exchange of message will be very slow. So we try to balance that activity. So how can you do it? Is there any possibility of coming across some or defining standards so that we can provide higher security, at the same time speed also will be in control? That was the big question. Because of lot of theoretical and experimental results, some recommendations are being done. The number of bits for n is multiplication of primary number p and q, should be at least 1000. This means that n should be around 2 raised to the power of 1024 or 309 decimal digits. The two primes p and q must each be at least 512 bits. This means that p and q should be around 2 raised to 512 or 154 decimal digits. The values of p and q should not be very close to each other. If they are very close to each other, then multiplication will be small value or some value. If the person somehow catches hold of p, which is public, then q can be easily calculated. To avoid it, it is always they should not be very close to each other. Both p minus 1 and q minus 1 should have at least one large prime factors. The ratio p divided by q should not be close to a rational number with a smaller numerator or denominator. The next recommendation is the modulus n must not be shared. The seventh recommendation is the value of encryption key E should be 2 to the power of 16 plus 1 or an integer close to this value. Eighth recommendation is if the private key D is leaked, Bob must immediately change N. Bob is the receiver. Alice is a sender. So the receiver must immediately change N as well as both encryption key and decryption key. It has been proven that knowledge of N and one pair of encryption and decryption can lead to the discovery of other pairs of the same modulus. Ninth recommendation is messages must be padded using public key cryptography standards and OAES. So all 8 must be used, and the ninth one, the public key cryptography, is the area of our focus today. What is public key cryptography standard? Why do we need it? Public key cryptography standard, and this PKCS aims at proposing a solution to the problems with small encryption keys. The formula of being used in encryption becomes weak. So we try to overcome this. That is, smaller the encryption key size, lesser will be the security. So the PKCS wants to address it. It tries to overcome the problems related to smaller encryption key size, and it wants to enhance the security. To do that thing, it has undertaken some task. And this PKCS uses the padding concept. Padding is a concept of adding bogus the digits in the message. PKCS aims at providing higher security to short messages. By using padding in a short message of a block of plain text with the random bytes, PKCS specifies the format of each block to be encrypted by RCA and padding. So whatever block means when we are having a plain text has been split up into many equally sized blocks, and each block, earlier it used to be smaller one, so that the encryption and decryption were becoming easy and security of the entire message was under threat. To overcome this, by making use of the padding concept, in PKS, random bytes have been pushed into the short message so as to make it larger. PKCS specifies the format for that, how you can actually enlarge the block. It specifies. When you do it, what are the things you have to carry out? PKCS specifies the format of each block to be encrypted by RSA, and for that purpose, it uses padding. Specify the format of each block to be encrypted by RSA using the padding technique. So by doing this, the size of the message becomes larger. Because of the larger size of the message, higher security can be provided. So PKCS format with padding a short message with random bytes in a block of plain text ensures higher security, because ciphertext will be a function of short message and also large sequence of random bytes. Now, for the person to hack, he has to carry out two things. One is he has to find out some function which can operate on the short message and recover it. And second one is he should also have another function which is working on large sequence of random bytes which has been used in padding. Because of this complexity of the PKCS, higher security is being provided. This PKCS uses trapdoor one-way function. PKCS uses trapdoor one-way function which states it is easy to calculate in one direction. For example, let us say encryption. If we are easily calculating on encryption side and infeasible to calculate in the other direction unless certain additional information is known, means the decryption becomes difficult, it becomes infeasible, it takes more time, it takes more effort, it requires higher level of mathematics. And if we want to do it something, then the additional information is known. With the additional information, the inverse can be calculated in a polynomial time. This is called trapdoor one-way function. If from the encryption side, if the calculation is easy, then for the decryption side, the calculation becomes almost infeasible unless otherwise certain additional information is known. But in public key cryptography, additional information is available at the receiver end. Because of that, he will be in a position to calculate, but other than him, the other unauthorized people, including the sender, will not be in a position to work on recovery of the message once it is in the form of ciphertext. The trapdoor one function family is a family of invertible function fk such that y, which is the function fk of x, means the function of the key on x, both k and x are known, then getting the value of y, which is a function of key k, and let us assume that x is some plain text, it becomes easy. The inverse of that, which is the inverse function of the k and the y value which we calculated earlier, to recover x value is easy if k and y are known. But however, what we are doing, the k has been split into two. One is public key and private key. Only the public key is known and other part is not known. And we are also using cyber function. The multiplication of the values of p and q there in a public key cryptography. Third one is x equal to the function inverse function of k and on y. If it is infeasible, it is going to be infeasible if y is known but k is not known. So when we are trying to implement public key cryptography, the private key, always we want to make it unknown. It is only should be available with the receiver, but not with the sender or any public. When we try to implement this PKCS standard and a format, what are the things involved there? That we can study now. PKCS number 1 is one of a set of 15 standards for public key cryptography developed by RSA laboratories. There are 15 standards that have been recommended by RSA standard. It is the first standard, number 1 within that PKCS. Like that, second standard, third standard, like that, totally 15 standards have been proposed by RSA for public key cryptography. It includes the format of each block to be encrypted by RSA, and it also includes algorithm independent syntax for many of the artifacts. Now we shall try to see how the entire formatting takes place. The PKCS format of each block to be encrypted by RSA includes the bytes of the block from left, most significant, should be 00. Means it starts with 00, followed by 02, which is in the hexadecimal format, and then followed by at least 8 random non-zero bytes. So 00, 02, then 8 random non-zero bytes, and another 00 at the right and end of the random byte string, which indicates the start of the plain text data section in a block. This extra has been padded there. So 00 followed by 02 followed by 8 random non-zero bytes, and then ending with 00. After that, plain text. This is the way. Padded plain text 0002. Then after that we are having total 8 random non-zero bytes. Then ending with 00. Then follow that, plain text will be there. This is padded plain text. Let us assume that we take unpadded message 000000 like that up to the end, then followed by plain text. We convert this unpadded message by adding up 00 to the leftmost, followed by 02, then the pad of random bytes, followed by 00. This is padded short message. After that, we added up plain text. Now what happened was, original plain text, which was small, because of this addition of the values here, which are 0 and 02, followed by 8 bytes, then 00, makes the entire earlier short plain text into large message. Now once we convert this, then what happened was, already we know that smaller the message, then lesser will be the security. The message, higher will be the security. So by using this format, we have made the original plain text block large now. Because of that, higher security has been provided. Now we have to send this particular the message in the particular format of PKCS format must be transmitted. So optimal for that purpose, optimal asymmetric encryption padding has been proposed, which helps us in building the algorithm of exchanging a message. What has to be done at the sender side, what has to be done at the receiver side, so as to convert the original message into the message to be transmitted along with padding. And after receiving it, how can you remove all the pads to recover the original message? That has been explained OAEP. The whole idea of OAEP is that when there is a concatenation of P1 and P2 is there, where P is a masked version of padded message, means the P will be having P1 and P2. That we concatenated that. So then it is being transmitted. When it is coming at the receiver side, the P1 is the padded one and P2 is the plain text which has been transmitted. So P2 is sent to all the receiver to find the mask. How it is working now? Let us see that. PKCS on OAP procedure side, sender. So M is the packet message. The message is less than M bits. So original message of plain text has been split into the different set of messages. So we have picked up M here, which is having M bits. Then one time random number R. So once the message is coming, how it is getting converted using the one time random number. After that, how we are going to pad the plain text P1 with the plain text P2 with the padded the value P1. Then arriving at the ciphertext, then transmitting over, which is comprising of public function k bit to m and m bit to k bit, because the message is having two parts. One is padded version, second one is the original message, which is falling between m bit to k bit. We shall be in a position to convert the message along with this padding and encrypt it and send it. So now look at the diagram. First message comes, then the message, from that message we pick up the block M with M bits, and then on this M bit we carry out the function. The first, the K bits, after that the second part we consider here M2 K bit. So first K bits will be converted or encrypted, and then it has been put in the form of P1. Then from the K bit to, okay, like this we converted now. So the first K bit to M bit have been converted, and that has been transmitted, and it is appearing as P1. Then by making use of the H function have been converted and they have been put into P2. Like this, the message is having M plus K bits. M bits are for padding, K bits are actually the original message. When both of these have been given to encryption, which is using the exponential function as usual in a public key cryptography, and converts into ciphertext. Now this particular message will be arriving at receiver. In brief, at the sender side the encryption takes place. The following the steps, what we are going to explain is defining the encryption process. The sender Alice pads the message to make an M bit message, which we call M. Please understand that when we say that the sender pads, means the person is not doing it. There is one algorithm that has been provided. As soon as the sender is actually trying to send some message, which is a short message and which is actually representing a fixed block, then encryption algorithm is going to add up, if it is using PKCS format, pass the message to make an M bit message, which we call M. Then Alice chooses a random number R of K bits. Note that R is used only once and is then destroyed, because unauthorized people should not access it. Randomly, this random number is being used, and this random number R is of K bits. Alice uses a public one-way function G that takes an R bit integer and creates an M bit integer. M is the size of M, capital M, and the random number which we used earlier should be smaller than the size of the message. And this is the mask. Means mask is nothing but the padded the bits that we have added up into the message that we are trying to send. Then Alice applies the mask ZR to create the first part of the plain text. Then modulus addition takes place, that is modulus addition ZR. P1 is master message, because the PKCS format expects that first we have to add 00, then 02, then following that 8 bytes, then following that 00. We have to add it up one by one using GR function of random number generation. We are going to add up after 0002 we are go on adding up the padded information here. Now Alice creates the second part of the plain text as P2, which is a function of H P1, then modulus addition R. The function H is another public function that takes an M bit input and creates an K bit output. This function can be a cryptographic hash function. Later, at some part of the course, we'll be discussing on that. P2 is used to allow Bob to recreate the mask after decryption. Bob is actually receiver side. Now, in general, Alice is creating the ciphertext C, which is using encryption, which is a exponential function on the plain text P, and this, by making a PKCS format, is actually P1 concatenation of P2 raised to P and sends C to the Bob. Like this, the original message along with padding, by making use of PKCS format, will be done by with the help of random number R, which is whose size is smaller than size of the message, is carried out, and modulus addition operations will be taking place here, and then we finally get C value, and this C value is getting transmitted over the message. I mean over the insecure the communication channel. Now it is arriving at the receiver end. What is happening at the receiver? The message C comes here. Message C is having two parts. One is with M bits, which is a padded message P1, and second one is key bits, which is representing the corresponding the information related to the plain text. Our overall objective is to remove the M bits and recover K bits, and from there we have to recover the plain text. So the C with M plus K bits has been supplied to decryption algorithm. Now in the decryption algorithm, decryption key will be there, plus plain text has been supplied as the input, and it knows the public key also. Now this particular decryption algorithm, it takes M plus K bits, which is combination of P1 and P2. And since it's a standard, it will be knowing the first M bits P1, and after that from after M bit up to K bit it is P2. Like that algorithm will be knowing it. So it separates out the M bits in P1, and after M bit up to K bits in P2, it separates out that P2 part has been supplied here, and then it will be inversely operated, and here using the H function and using G function, it has been calculated. So it has been recovered. The P2 has been removed from the part. The P1 is being passed and recovered to the receiver. Means once the ciphertext C is coming at the receiver side, because of the PKCS standard, the decryption algorithm will be knowing that the message that has come is having P1 and P2. The first P1 is actually padded information, which is not required. It has been provided only to give additional security, like that it will be knowing. Second P2 part is a original message which we have to recover. So because of that, the P1 will be removed from the text. P2 only will be considered. On that one, we are performing the reversal or inverse of the operation of Z, and then we get the information. Then that information will be, from the digital form, will be converted into the plain text form, and it will be provided to the receiver. This is the overall thing which will be happening here. So decryption side, it shows that the Bob creates the plain text by making use of decryption key on the ciphertext. Based on that, the P1 concatenated P2, this message will be obtained. Bob first recreates the value of R using the function P1, then modulus addition P2 equal to P1, then modulus function P1 plus R equal to R. Bob uses the function G on R, then modulus addition P equal. So the function on R, then modulus function on P. This shall be equal to the function G on R plus modulus addition of GR and plus modulus addition M equal to M to recreate the value of the padded message, and this will be removed off. The value of padded message will be removed. After removing the padding from M, Bob finds the original message. Like this, on the receiver side, activities will be happening. This PK standard and also PKCS, these procedures, by making use of OAP, are very popular. They are being standardized. So in public key cryptography, many new type of algorithms and differing implementations have originated, but they have got roots in the format of the public key cryptography standard, and also they have got roots in OAP procedure. In summary, standardization has been ensured, which helps implementation both on encryption side and decryption key. And also in the entire activity, by using the padding concept, we have made the message larger so that any hacker cannot easily decrypt it. And then we implemented the entire activity properly. Forward side, it should be easy to calculate. Reverse side, it should be difficult to calculate. That is the technique we have used. This is the overall PKCS related format and OAP procedure, both on sender side and receiver side. With this, we come to the end of session 5 of module 10. Thank you.